So the velocity would be 3.8 or 3.9 seconds. Now, what would the velocity be? Well, it's going to be very close to 47. So we might say the average velocity is about minus 45 meters per second, a little bit less than the 47. Interestingly enough, it looks like it's a similar average velocity as the other, or the impact velocity would be similar to the other. All right, so that's how we would do this with an average velocity table. Now, moving to our analytic solutions, we know our velocity is equal to the acceleration minus 10, and our initial velocity is minus 7. So this is our model that will give us the velocity for any instant in time. With our z, we have z equals 1/2 minus 10 t squared plus a minus 7 times t, and we'll make our initial position 0 again. So that's minus 5t squared minus 7t will give us our vertical position. So these are our two equations. And again, from the previous, we set this equal to 0 and this equal to minus 100. The positive is the up direction, the negative is the down direction. So when will it hit the ground? It will hit the ground when z equals minus 100. So when is minus 100 equal minus 5t squared minus 7t? Aha! This is not something we can easily solve. We can add 100 to both sides and use the quadratic formula. Let's see, x equals b plus or minus the square root of b squared minus 4ac all over 2a. Yuck! We have a tool we can use for this. Now, we have our equation, which is z equals minus 5t squared. That's the z of the rock. The z of the ground is equal to minus 100. So we want to know when these two things meet. Graphically, this is an intersection. So we go to our Desmos, and we already have that there, but it's now minus 7x. That's actually the only thing that changed. The position of the ground is minus 100. And we look at the scaling here. And we can see that it's, between 3.8 and 3.85, maybe about 3.825 seconds. So now, on our answer paper, we can just say that t equals 3.83 seconds. And that's sufficient. We can go from this to this and just give this answer. We don't need to show any work for how we got it. Beyond this, we've gotten to that point, and now that's our answer. So that will tell us how long it will take. And now the impact velocity minus 10 times 3.83 minus 7. So that's minus 38.3 minus 7 is minus 45.3 meters per second. And notice that answer is very similar to the other one. And previously, it was 44.7 meters per second. So we can see it's a little bit faster, and it's 3.8 seconds instead of 4.4 seconds. Right? So minus 45.3 meters per second versus minus 44.7, 3.8 seconds versus 4.47 seconds. So indeed, it takes less time. And indeed, it will have actually a higher impact velocity. Although, interestingly enough, we couldn't detect that from the table. It looked like they were the same. So that's how we'd solve a problem of a rock thrown downward, both using the average velocity table and the analytic table. Now, again, to get to our graph, our VT, it has a y-intercept of minus 7, and it will have a slope of minus 10. The things we can read off a velocity time graph are the axes. The gradient, delta V over delta T, is the acceleration, which is minus 10. And the area, V delta T, is the displacement, delta Z. So this was the curve for V0 equal to -7. If we were to graph the drop, it was here, like so. And this is for V0 equal to 0. Notice for both of them, the acceleration should be -10, so the curves are parallel. Curves are parallel. Now, when it comes to the position time, our z and t, our function we're looking to find out when it meets -100. And the curve we just had looked like this. 3.83 seconds. And the prior example, well, let me change the color of that so it matches. -100 looks like so. And our curve looked like this when it reached a position of -100, and that occurred at 3.83 seconds. The other curve took longer, 4.47 seconds. So you could see then that it has a broader, kind of a broader arch to it. It has a smaller concavity, if you will. So you can see here it's going to take longer, which makes it broader. So the effect of increasing the velocity, the effect of increasing the initial velocity is to make it get there faster. And so if we were to increase the initial velocity to say, oh, maybe the V0 is -12, well, then it might look more like that. And if we were to increase it to -20, it might look more like that. So you can see the time is getting less, and the shape of the parabola changes accordingly. In the next installment, we'll look very deeply at what happens when we throw it upward.